We're back again. This is our area lecture number 2. So hopefully you're watching this on Thursday. Aren't the streets a mess today? Before I do the new stuff, what I would like to do is to go take a look-see at the thing you ended up with yesterday. Remember, this was from the 2000 AP free response questions. And this was question number 1, and the task was to find the area bounded by these two curves. And I had mentioned that when you're doing this, you're going to be using your calculator, but there's probably something even more important, and that is to try to duplicate this picture on your calculator. I think that's you don't have to do it, but I think it's really, really useful. So if we look at that top curve, I'm going to call that E to the negative x squared, and notice that that is the exponent of the exponential. And the second curve is this 1 minus the cosine of x, and that's the second curve. And then to make sure I've entered it in correctly, I want to look at the window and mimic the window. So it looks like on the left side here, this is about minus 1/2. So I'll make that my x min minus 0.5. The x max is just on the other side of 1.5, 1.6 maybe if you want. The x scale is every half, right? So obviously there's a tick mark here and here and here. So x scale is 0.5. For the y's, the smallest y is a little bit below the axis. I'm going to call that negative 0.3-ish. I'm not sure it much matters how far down you go, but negative 0.3. The max y is 1.5. The y scale is again 0.5. And then when I hit graph, I should get a picture which is similar to the one in the test. And it does look about like that, this being R, the region in here. Why would you want to do this? Well, I mean, devil's advocate, let's suppose for some reason you were in degree mode instead of radian mode. Shame on you. But when you were to graph this, I see the exponential and I have no clue what happened to the second curve. So if I was trying to trace along, there's the exponential, there's the second curve. You go, wait a minute, where is it? I don't see it. Well, you're in degree mode, not radian mode. Let's put it back in radian mode. And now all of a sudden it is there. And if I trace along, there's the exponential and there's the trig function. Okay. The other nice thing about doing this, of course, you need to get this point of intersection. And I had mentioned at the end of the first video that this is not 1. This is some number a little bit less than 1. So if you have the graph here, you can find second trace intersect. You can find that point of intersection pretty easily. Bang, bang, bang. Gives you the intersection. And yes, you can write that down. So on your page, you could write that top value is 94194,408. That's this point here. But it's much easier just to store that in your calculator. So exit out of here, hit X, that value comes up again, and then store it. I'm hitting the STO arrow. Store it as something like alpha A. Okay, so that's that top value. Now, when we go to work the problem and we say the area is an integral from 0 to A, and now we can say the top curve we called y1, the bottom curve we called y2 dx. This will allow us to get the area very easily. Now, is this legal on the AP test? Yes, as long as you state what y1 is. y1 was that exponential, e to the minus x squared, and y2 was 1 minus the cosine of x. So if you wrote that down, then you could reference y1 and y2. We notice on the problem, they were not called f and g. If these were actually given as f of x equals and g of x is equal, and that was given on the test, on your work, you could actually say, you know, the integral of f minus g dx from 0 to a. Again, we should probably reference, you know, what is a. We have to say also in our work, if we're going to be using the letter a, we're going to have to say somewhere that A is this number, wherever it was, 0.941944, and some change. So if we've done all of that on our paper, then we can easily determine the area on the calculator. In fact, I'm not sure you could do this by hand. You don't know how to find the antiderivative of this exponential. That's one that you don't know how to do. But we have it all written down. You go to your calculator. So we've got math 9, the integrand, we had y1, vars, y vars, function y1. Take away the second one, vars, y vars, function y2. That's our integrand. Our variable is x. We're running from 0 out to a, right? And that's the answer. Okay, so when you looked at the solution, I assume you did, and they have this 0.591, right, to the nearest thousandth. That's how you could do it very easily. The calculator does the integration, and it makes it much, much easier to key in, assuming you've graphed y1 and y2. Okay, so anyway, that's wrapping up lecture 1. But let's go and do the new material here. What I want to do is I want to look at example 2 in your book. Example 2. Because it's very similar to what we just did, except now we're going to be doing it by hand. And what I mean by that is if you look at example 2, it says find the area of the region. Area of the region. Example 2. Back in your book again, 464. And again, if you didn't bring your book, remember I've scanned this in for you. Area of the region enclosed by the graphs of y is equal to x plus 6 and y is equal to x squared. So little sketch again. We did this in the first example. We noted the parabola was looking like this and the line was looking like this. And we had already found the area running from 0 to 2, right? So this was example 1, finding this area. But now they want the entire area, and they don't tell us the right-hand boundary. We don't know this number, nor do we know this number over here. And yet we're supposed to find this entire area enclosed by that entire graph. Okay, so to do this, we need the point of intersection. Now, the one we just did on the calculator, we found the intersection on the calculator, but suppose we didn't have a calculator available because there are some problems where a calculator is not permitted. Well, to find a point of intersection, you set these equal to each other. So x plus 6 has to equal x squared, or moving everything to one side, you have x squared minus x minus 6. Notice it factors very nicely. X minus 3, x plus 2, basic algebra there. So x is either going to be equal to 3 or x is equal to negative 2. And in fact, those are these numbers here. This is x is equal to 3, and this one is x is negative 2. Okay, so once we have those right and left bounds figured out, then we can calculate the area just as we did before. The area is the integral. The left boundary is negative 2. The right boundary is 3. The top curve is x plus 6, and the bottom curve is x squared. So we'll take that difference and then integrate with respect to x. We had already done the antiderivative. If you remember that, we had x squared over 2 plus 6x minus x cubed over 3. That was the antiderivative in example 1, same antiderivative here, but now we're going from negative 2 to 3. So parentheses minus parentheses, a little bit more arithmetic because the lower limit's not 0. But we've got 9 halves plus 6 times 3 is 18 minus 27 thirds. And then on the bottom half, just be careful, you're squaring the negative 2. So that's 4 over 2. Negative 2 times 6 is negative 12. And then you're cubing negative 2, which is negative 8. So that's negative 8, which is plus 8. thirds. So we've done all of that. There's our answer. It's not simplified. It is correct. We could leave it that way if this were a free response question. Let's go ahead and finish the arithmetic just to say we did. We have 9/2 plus 18, and this is what, minus 9, and then minus 2 distributing here. This is plus 12, and then minus 8/3. So if we just deal with the whole numbers, let's see, that's 9, that's 10, so 9 and 10 is 19, plus 9/2 minus 8/3, common denominator is 6. Why don't we make this a little bit easier? This is 19 plus 4.5. I hate to use mixed numbers, but minus 2 and 2/3. So what do we have? 19 plus 4, take away 2, and then plus 1/2 and take away 2/3. So that just makes the fractions a little bit easier to deal with. 19 and 4 is 23, take away 2 is 21. And then, so this is 3/6, take away 4/6. So we have 21, take away a 6, or 20 and 5/6. So what's that, 125/6, right? 6 times 20 is 120 plus 5 more, 125/6. And looking in the book, page 464, yay, we did the arithmetic right, 464. Yay. Okay, so that's example 2. Example 3. Example 3 takes an area problem and turns it on its side. And this is sort of like a new idea, so new material here. Example 3 has the parabola x is y squared. Now remember, from algebra 2, that's a sideways parabola going that way. And we have the line y equals x minus 2. Well, that's not too hard. That's a y-intercept of -2, x-intercept of 2, and the line looks like this. And the task is to find the area of the region enclosed by the parabola and the line. So now we're looking for this region in here. And we're going to be using what he calls method 2. Where are we looking at? Let's see. I'm flipping through the book here. Yeah, this is on page 466. Page 466. This is the second area problem. So look at the box there. And just noting, he says you have a picture where you have 2 curves, and he calls them x is some function of y, and he calls this one x is some other function of y, v of y. And then you have a boundary up here. This is y is equal to d, and another boundary down here. This is y is equal to c. And your task is to find the area enclosed. Area enclosed. And this time you're not going to be integrating with respect to x, as in the first area problem, but you're going to be integrating with respect to y. So you sort of have to think of a little horizontal box here. And you're going to be moving this box up and down, and you're going to sort of like cover the entire region with that box. And if you just look at the formula, the area is going to be an integral once again. Now we're going to have y running from C, y running to D. So these are the boundaries here, right? Top and bottom of the region. And then for the length of the bar, you're going to have to figure out how long this is. And this is going to be the W function, and then take away the V function. So that's the integrand, and then you integrate with respect to y. So this looks a little strange what's going on here. Let's see how it plays out in this problem, and then I'll give you a simpler example, and then we'll look at a free response question. So we've got a number of pieces of work to do here. Okay, so as we look at our picture, we say we have this horizontal length here. And as I run this from top to bottom, I note that the right arrow is always on the line and the left arrow is always on the parabola. So we have sort of a consistent definition. The right arrow is always on this line every time, and the left arrow is always on the parabola. A nice simple way of describing this region. Go from the parabola to the line every time. Go from the parabola to the line horizontally. This is called a horizontally simple region. Horizontally simple region. Okay? And whenever you see that, then you're going to be using this second area problem. So let's see. The area is going to be an integral. The bottom of this region is this number right here, which we'll have to figure out. That works out to be -1. The top number, way up here, is going to be where these guys hit. And if you look at the text, it says in example 3, this hits up here at 2. So I'm just going to throw those numbers into my problem here. Y is running from -1 to 2. Now for the integrand, I need the right-hand side. I need to know the equation of this line. I need to know what this is. Now, before I go any further here, let me just come back to this in a second or two, but I need to get a basic idea. If I have a yardstick and say this is the x-axis, and this is 5 and 6 and 7 and 8 and 9 and 10, and I want to figure out how long something is. Say I want to figure out the length of that horizontal distance. What I need is I need the x-coordinate here, and I need the x-coordinate here, and I need to subtract those. So the length of that bar is going to be 10 minus 7. So it's the x-coordinate on the right, take away the x-coordinate on the left. That's how you find horizontal length. So let's go back here again. If we want to figure out the horizontal length of a typical bar, I need the x-coordinate here, and I need the x-coordinate here, and I'm going to subtract those two. Now, obviously, it's varying. These bars are all different lengths, but the description of the x is pretty consistent. So, for example, on the left side, we know that x is y squared. That was given to us as the equation of this parabola. The left side is always going to be y squared. What's the equation for the right one? Well, we were given this. I don't really want to know what y is. I want to know what x is. So just solve this for x. X is going to be y plus 2. X is y plus 2. Now, to find the length of this bar, and that's what we're going to be putting in as our integrand, you need to know this x-coordinate, take away this x-coordinate. So a little bit of discussion there, and please read the text. You might have to read it a couple of times. I'm going to get y plus 2, right? That's the right-hand x-coordinate. I'm going to take away the y squared. That's the left-hand x-coordinate. And then I'm going to integrate with respect to y. Okay, so that seems a little bit of challenging to do. We don't have to do this often. There are problems that are better suited by integrating with respect to y, and this is one of them. Okay, let's go back to your class page for a sec. When we look at the free response questions, and we look at 1999, right, the area question here, open that up, okay. The area question here is number 2, and we have to find the area bounded by the graph of y equals x squared and y is equal to 4, right in here. Okay, so we're going to find that area. And that's not too terribly hard. A little sketch here. This is y is equal to 4, and this is y is equal to x squared. Now, is this an area problem type 1 or type 2? And the answer is you could actually do it both ways. If we think of a vertical bar running in here, and I want to figure out how long these are. This is the type 1 problem. You need to know the y-coordinate here, which is 4, and you need to know the y-coordinates here, which are always x squared. So if I want the length of this bar, it's always going to be 4 minus x squared. That's the length. And then I can integrate dx, and x runs, I think, in this one from -2. You would have to verify this. This is -2 to 2. So -2 to 2. And that will give me the area of that region. Could I do it running left and right? And the answer is you could. So let's see. I'll do a couple of tricks here just to make this a little bit easier. Here's my area. And I've got, this is y is equal to 4. And this is y is equal to x squared. Or if you will, x is equal to the square root of y. That's this. And obviously I'm taking away half of it. I'm just going to be finding half the area here, then I'll double it. But now I want to think about how would I calculate the area using horizontal rectangles or horizontal bars. Okay, so I would need to have the x-coordinate here. There it is. I would need to have the x-coordinate here. X is equal to 0. Remember, that's the equation of the y-axis. X is equal to 0. So yeah, I could do these. The length of this bar would be the square root of y minus 0. The right-hand x-coordinate, take away the left-hand x-coordinate. The width is dy, and I'd be stacking these up. The bottommost bar is way down here at y is equal to 0, and as they go higher and higher and higher, the topmost bar is y is equal to 4. So this integral will also give me the area. Well, it gives me half the area. Then I would have to double it to get the other half. Okay, so some problems you can do either way. Either way. Let's go back to the free response questions again. I want to try to find one that's going to be better served by integrating with respect to y. So here's 2001. I'll just take a glance at this area problem. Okay, let's see. R and S. Ooh, class is almost over. Okay, so find the area of R. Find the area of R. And when we look at R, this is a small picture, but you can sort of imagine what's going on here. If you're trying to find the area of R, that may be difficult to do with vertical bars. This is not a vertically simple region. As you move from left to right, you start off with the top being along this curve, but then all of a sudden the top changes to that curve. Not vertically simple. It is, however, horizontally simple in this sense. Okay, so if you look at this and you want to run horizontally, the right side is always this curve here, and the left side of our bar is always going to be this curve here. So this is a horizontally simple region, and we could find the area of R by integrating a bunch of horizontal rectangles. Okay, so I'm going to suggest that you try that one. By the way, the solutions to this are on the class page. You can look at the solutions, and I think when you look at the solutions, you'll find there's two different ways of doing this. In fact, there's probably more than that. But one way would be to integrate with respect to y, as long as you knew how high to go. You'd have to figure out how high that y coordinate is. This screams calculator again, because I can't solve this equation without a calculator. So there's two more area problems to play with, R and S. And by the way, when you look at S, that one is vertically simple. So as you're finding the area of S, the top is always this function, and the bottom is always this function here. So for the area of S, part B, I would certainly integrate with respect to X. Okay, so other problems out of the book. In your textbook, you should be able to do problems 3 and 4. So page 467, 467, problems number 3 and number 4. Both of these are designed to be integrated with respect to y. So for number 3, just looking at it, it seems pretty obvious to me that here's the picture of number 3. You've got a region which is not vertically simple but is horizontally simple, right? So you would need to figure out how long these guys are, and then as we stack them up down at the very, very bottom, it looks like we're going from 1, y is 1. This is over here at y is 1, and then as you stack them up, it stops right here, which is y is equal to 2. So y is equal to 2 dy. And then just make sure you can figure out how long this is. You'll need to know what this x is, and you'll need to know what this x is. They're variables, obviously. And then you should be able to figure out the length of that bar by doing this x minus this x. Okay, so play with 3 and 4. 4 is a similar type of problem. Both of these solutions are in the solution manual. Okay. You need to warm up, go up, have some hot coffee, hot chocolate, and then go shovel the walk again for your parents. Okay, let me go ahead and stop this one here. We're 26 minutes in, and I'll put one more together, and we'll look at some more free response problems out of the AP test.